octet means that you have more than 8 valence electrons around the central atom. So my first example here is SF6. And if I draw sulfur's dot diagram, it's in group 16, so it has 6 valence electrons. So normally, I'm going to have my 4. I'm going to come back around with 2. And so I only have 2 places it can bond. If I have 6 fluorine, that doesn't work out. So what happens with sulfur is it expands its octet, and it is going to separate all 6 of those electrons. Now, when we draw these, we are drawing a two-dimensional shape. So it actually doesn't really matter where we put our stuff around the central atom, because we're going to learn here in a couple lessons about three-dimensional shapes. So how you space these out really doesn't matter. We just know it's going to take more than just our normal 4 sides for this to happen. So then what happens is each of the fluorines can now come in with their 7 electrons, and they're going to make a bond. So each fluorine comes in, makes a bond. And then we're just going to do that over and over and over. Now on this one, I skipped a step and I forgot to write how many total valence electrons I have. So each of the 6 fluorines have 7 valence electrons, plus my sulfur, which has 6 valence electrons. So I am looking to have 48 total valence electrons from this. So if I check, I have 2, 4, 6, 8, 10, 12 around sulfur, which is okay because it can do an expanded octet. The way it does that is it uses the empty d orbitals to shift electrons around in it. It's an unusual thing that can happen, but sulfur and phosphorus can do that. So then if I count, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. So I've used all my electrons for this one. So you're going to do sort of the same concept for phosphorus. Again, normal phosphorus has 5 valence electrons, so we would draw it like this. It can only bond 3 times. I've got 5 hydrogens, so that's not going to work. So again, phosphorus is going to spread out its electrons, and hydrogen is going to come in and bond to each of those lonely electrons with its 1 electron. Again, I am skipping the step where I'm showing all of the electrons. I'm just bonding them with the single bond. And phosphorus has 5 valence. Each of the hydrogen has 1, so I should have 10 total electrons. So I have 2, 4, 6, 8, 10. Hydrogen's 1 and done. Phosphorus has 2, 4, 6, 8, 10 around it, but that's okay because phosphorus can do that expanded octet. So then my next one is going to be unusual because it is a noble gas. And in the noble gases, xenon and krypton can be forced to bond, but helium, neon, argon can never, ever, ever, ever bond. They cannot do that. And then krypton, xenon can, and then radon is so radioactive that it decays very quickly, so we just don't see it in chemical bonding. So in this, I have 7 times 4, which gives me 28 for my total from fluorine, plus my 8 from my xenon. So I actually have 36 electrons. Now, this one's going to do it a little bit different than these two did because it already has 8. So xenon by itself looks like that. And so it already has 8. There's no lonely dots. There's nowhere for it to bond. I don't have 8 fluorines, I only have 4. So typically the way that you'll see it drawn is they will bring in a fluorine on 4 of the sides, just like our normal northeast, southwest side off of the central atom. And that has used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I have 2 more electrons that I need, 4 more electrons total. I'm going to do 2 pairs of electrons. And they typically draw it like this, where off of the central atom, we're going to have our 1, 2, 3, 4 bonds. And then off of that central atom, you're going to draw in the extra dots as unshared pairs. And they typically do it just across from each other on either these 2 sides or on those 2 sides. And by doing that, I've used my 36 total electrons. Fluorine is balanced. It's already bonded and it's done. And then xenon is doing 2, 4, 6, 8, 10, 12. It has an expanded octet because it already started with 8. And so again, that is unusual, but it is something that can happen. So then we've only been dealing with single bonds. There are double and triple bonds, and those are going to share more electrons. Double shares 4 and triple shares 6. Remember, we talked about the bond energies in a previous lesson. And so we talked about how single, double, triple bonds are going to have different energies. It is going to take more energy to break a triple bond than it is to break a single bond. And it's because they're sharing more electrons. So when we do these multiple bonds, the only time we do it is whenever there just aren't enough electrons to make everything stable with that 8 valence electrons. And so we shift the electrons around until all the elements are stable. And so we have 4 examples here. So let's start with CO2. So again, let's count up how many total we should have. So each oxygen has 6, so that's 12, plus carbon has 4, so 12 plus 4 gives me 16 electrons. If I draw it and do a normal skeleton structure, I'm going to put carbon in the middle. If carbon is an option, carbon is going to be your central atom. And then you sort of want to just make it symmetrical. So over here, I'm going to put an oxygen with its 6 electrons. Over here, I'm going to put another oxygen with its 6 electrons. This is going to form a single bond and a single bond. So I have used 2, 4, 6, 8, 10, 12, 13, 14, 15, 16 electrons. So I've used all of my electrons, but the problem is nothing stable. Oxygen right now has 2, 4, 6, 7, 8, 2, 4, 6, 7 around it. Carbon has 2, 4, 5, 6 around it. So this is what happens is whenever we have these lonely dots that aren't being used in normal bonding, they are going to shift around and be used in multiple bonding. So what's going to happen is this electron and this electron are going to be taken and they form a double bond. This electron and this electron are going to be taken and they form a double bond. When that happens, I use 2, 4, 6, 8 around oxygen, 2, 4, 6, 8 around carbon, and then 2, 4, 6, 8 around the other oxygen. I've used all 16, no more, no less. And on these, you can start out with just the skeleton structure. Some people just start by getting the skeleton structure done, and then you can erase and move those electrons like I showed with that. And some of these don't always work out perfect. Like it's not always these 2 being shared. Like sometimes it might just be one of these electrons has to come over to this side. Sometimes it's not going to be as pretty as that problem was. So now let's do N2. So each nitrogen has 5 valence electrons, so there's a total of 10 electrons that I need to do something with. And so since there's only 2 elements, all they can do is bond with each other. Nitrogen has 6 valence electrons, so I have 2, 3, 4, 5, and then 2, 3, 4, 5. And so I've used my 10 electrons. Neither nitrogen is stable. So again, I'm going to shift my electrons, make a double bond. Still have lonely electrons, still not going to work, so I got to shift these and make a triple bond. Once I've done that, I've used 2, 4, 6, 8, 10, which is how many I have, and it has a triple bond between each of the nitrogens, and there's no lonely electrons anymore. H2CO. So oxygen has 6 valence electrons, carbon has 4, each hydrogen has 2, so that's 6, 10, 12 electrons. Central atom, if carbon is an option, carbon's going to be a central atom. And then again, you just sort of want to distribute everything around so it's sort of even. So I'm going to put a hydrogen over here. You want to make it as symmetrical as possible. There's more science behind why it does this, but for right now, just make it symmetrical around it. We'll talk more about that in the next section. So oxygen comes in with 6. So 2, 4, 5, 6. And then I have this electron around here left over from those 4. So hydrogen's 1 and done. I've used those. I've used 2, 4, 6, 8, 10, 11, 12. Carbon and oxygen are not stable, so I'm going to take an electron away from each of them. Do a double bond, so I have 2, 4, 6, 8, 10, 12, and around carbon I have 2, 4, 6, 8, and around oxygen I have 2, 4, 6, 8, so everything is stable. Normally I would erase those dots, but on this tablet, when I'm drawing, it's annoying to have to erase, so I'm just Xing them out. I would not leave the X's there in a full Lewis dot diagram. So nitrous acid, which is HNO2, has 2 nitrogen to oxygen bonds. These bonds have different lengths. The hydrogen atom is bonded to one of the oxygen atoms to draw the Lewis structure. I have tons of typos in that sentence. Sorry about that. So what this is telling us by saying that these bonds have different lengths is that one of them is going to be probably a single and one's going to be a double. So again, I'm going to put my central atom in, which in this case is going to be nitrogen because it can make 3 bonds. I'm going to distribute around my electrons. So I'm going to bring an oxygen over here and an oxygen over here. It tells me that I need to, the 2 nitrogen to oxygen bonds are going to be different lengths. Whoops, I put too many dots here. Not sure why I put it down on the bottom. It says these 2 are going to be different lengths, which means that one is going to be single and one is going to be a double. Let's count up our total electrons and go from there. So I have 6 oxygen, 6 electrons for each oxygen. So that's 12 plus 5 from nitrogen plus 1 from hydrogen. So I've got to have, by the end, 18 electrons. So right now I have 2, 4, 6, 8, 10, 12, 14, 15, 16, 17, and I haven't even brought in my hydrogen yet. And so it tells me that my 2 nitrogen to oxygen bonds, these bonds have different lengths. It says the hydrogen bond atom is bonded to one of the oxygens. Okay, so it really doesn't matter which one you choose. I'm going to choose this one. So I'm actually going to shift these 2 electrons over to this side and then do my single electron on this side so that I can add in my hydrogen. So I'm going to add a hydrogen over here. When I do that, now I have 2, 4, 6, 8 around this oxygen. So this is going to have to be a single bond because you cannot have more than 8 around an oxygen. It is not an expanded octet. So I have 2, 4, 6, 8 there. I have 2, 4, 6, 7, 2, 4, 6, 7. So again, I'm going to move these 2 into here and I'm going to make a double bond. So now this fits all the conditions it told me. It says it has 2 nitrogen to oxygen bonds. So this is 1 nitrogen to oxygen. This is the other nitrogen to oxygen. These bonds have different lengths. This one would be longer. This one would be shorter. Because remember I talked about how it's like having a rubber band. It shrinks them together a little bit. And then the hydrogen atom is bonded to one of the oxygen atoms. And so this would be the complete structure. And like I said, I would never leave these things in. I would always erase those out in my final Lewis diagram. So when you're doing Lewis diagrams, it is a puzzle. You start somewhere and you just keep working until you get to the end. I would always recommend using a pencil when you're doing these because you're going to make a mistake and it's easier to erase and go from there than it is to use a pen and have ink everywhere.